All right, so we're going to look at solving trig equations, maybe a couple inequalities, we'll see, but mostly equations graphically. So the idea you want to keep in mind is that if you can find one solution to a trig equation, how many solutions does it actually have? Yep, infinite. If you find one, that one repeats forever, every single what? How often do answers repeat in trig functions? Every period, whatever the period is. Could be 360, could be 180, whatever it is. So, to solve it, find all the solutions in one period first. So, even though we're going to use the calculator, you'll still have to know how to find the length of one cycle. Because if you don't set the window correctly on the calculator, you're not going to get the right answer. And then you represent all solutions by putting the plus period times n. That's what I'm saying right there. Take into account the period, the repetitive nature of the function. So I'll just put, you'll have a solution plus the period times n. And how many solutions you get kind of depends on the equation. When we start raising trig functions to higher powers, we can get 2, 3, 4, 5, 6 solutions just in one cycle. I think last night the most you had was 2. We can definitely get more than 2 today. All right, now we focused on how to do this algebraically last night, doing the inverse sign, getting that answer, finding the reference angle, and then adding, subtracting, using one of these formulas. This one, let's just focus on graphical today because that's what we're doing. So if I want to solve this graphically, what's the first thing I have to do? About Chris? What do I have to do to solve this graphically?
You have to find all solutions in one period first.
Okay, so how do I got my calculator on, how do I do it?
You have to do x by itself. Probably. You take the sign point over point.
So you don't have to do anything to that by hand. We don't have to do any algebra with it. If you were going to do algebra, you take the inverse sign on both sides and go through all that stuff. But today, you can leave that just the way it is. Yep?
You graph sine 1 and y1, you graph y2.
Yes. Graph sine of x in y1, graph 0.8 in y2. Now, what would I do next? You got to be careful here. Yeah?
Set your window.
Yes. Set your window. So this goes in y1, this goes in y2. Next step, set your window. We want to set our window so that we find all the solutions, I wrote it on the previous page, in one cycle. So if we're dealing with sine, what's the length of a cycle for sine? And this is just the regular sine. We haven't done anything to it. Yep.
2 pi.
2 pi. So she said 2 pi. That means we're going to go with radians. You could have said 360 and we could have done degrees. We'll do it in radians. On the test, I'll be very clear whether it's degrees or radians. This problem doesn't say. I'll just add it in. Do it in radians. All right, so we're in radians. So the easiest way to get a cycle that's 2 pi is 0 to 2 pi. You can use anything you want for your min and max as long as the difference between them is 2 pi. You could do 2 pi to 4 pi. You could do 11 pi to 13 pi. It's kind of weird. I would just stick with 0 to 2 pi. The scale, that doesn't really matter. That's just how often you're going to see tick marks on the screen. I'll put a tick mark every, at the quarter marks. So every pi over 2 radians. How high and low is it going to go? It's just going to be -1 to 1, so that's fine. So you're going to see a tick mark at each quarter. Quarter, half, there's your 3/4, and then the whole. So now I've got my graph. Set my window. What's the last thing I have to do now? Yeah.
Find intersects.
Yeah, find both intersects. So now, calc, intersect. All right. So the first answer, when Chris was mentioning doing something to both sides of the equation, this is the first answer you would have gotten if you had just taken the inverse sine of 0.8. I think that actually would have been a lot faster. But we're just focusing on graphing today. So 0.927. We're not done with the 0.927 yet. I'm just writing it down. And the other one, well, I can probably find the other one quicker in my head than doing the intersect. I think in my head, the other answer is in quadrant 2. It's pi minus 0.927. I'll do the intersect, but I already know it's going to be about 2.21. I think the intersect takes longer myself. But 2.21. We'll go one with this one. 2.214. Now, each of those answers is going to repeat every cycle. And Kathleen, what did Natalie tell us the cycle was for sine? 2 pi. So that's where you put plus 2 pi in. Plus 2 pi in. And remember, n is an integer. That's going to be true in every time we write n today, so I'm not going to keep writing that. N is an integer. Questions on that? It's pretty easy to find the period because the trig function was pretty basic. 2 answers, that's pretty typical for a sine or cosine function. You usually get 2. Right? All right, so if you have a trig function, like we just had, and you set it equal to 0, all you're doing is you're finding the roots of the trig function. Okay, I'm just reminding you that when you set something equal to 0, it doesn't matter what kind of function it is, you're finding the roots. Okay, we've said that like 3 different ways. Finding the roots, finding the x-intercepts, finding the zeros. Okay, we've done it before. You don't really need to worry about the second part. I'm just reminding you that if you find roots in one cycle, those roots are going to be repeated every single cycle because they're periodic, right? So, in other words, if you've got a graph like that and it crosses the x-axis right there, well, it's going to cross the x-axis again every single cycle. Okay, exactly 1 cycle later, it will be crossing the x-axis again, and 1 cycle earlier, it was crossing the x-axis as well. Okay. All right, so that's not really critical. All right, so this is just explaining for like the 3rd or 4th time how you write all solutions. So again, find all the solutions in one period. How are we doing it today? Second calc intersect. Maybe you'll have to just do it twice, like the last one. I think one problem we got to do it up to like 6 times. It's not hard, it just gets kind of annoying at that point. So I already have the answers written for that. So find all the solutions in one period. And then the way you represent the solutions in general is take your solution plus the period times n. And you have to do that for every single solution. Plus period times n. Okay. And that means n is an integer. if you want to read it properly, it says n is an element of the set of integers. So it can't be a decimal. Okay, so what we just did right there is exactly what we just did right there. Okay, just keep it straight if you're in degrees versus radians. Okay, if the problem uses pi for period, then you're doing radians. If you've got like 180 or 360, that's probably degrees. Okay, so questions on that idea? Only time you don't have to put plus period times n is if they specifically say in the directions, find all the answers just in the first period. If they write, find all solutions in general, then you got to do plus period times n. Okay. So just read the directions. All right, so we know how to find, hopefully, the period of a single trig function. Like a single sine, a cosine, a tangent. But what if you have something like this? What if you've got something like this has a period to it, and this has a period to it? So how do you figure out what the period is of that whole thing? Well, the first step is to find the individual periods. Tell me the period of cosine squared, which we don't know yet how to do, and tell me the period of sine. Find each one individually. Then the period of the whole expression is the least common multiple. So the period of your entire equation is the LCM of the individual periods. Okay, so just to be clear about LCM, let's say I'm just going to make up numbers like 2 and 3. If one of your terms had a period of 2 and the other one had a period of 3, the whole thing has a period of 6. 6 is the least common multiple of 2 and 3. If you're not sure what the least common multiple is, you can always just make a list of multiples. List out all the multiples and then find the smallest one in each list. 6. Most of our periods are going to have pi in them, okay? But it's going to be the same idea. Find the LCM. Any questions on what I mean by finding LCM? Okay. So to figure out the period of cosine squared, we're just going to kind of play with it on the calculator and look at it and see if we can figure it out. Eventually, I'm going to give you a formula for how you can find the period of any trig function to any power. And it really has to do with whether it's an odd or an even power. Is there a question?
Yeah, just like for the LCM, for the pi's, do you just leave it?
Yeah, so let's say one of your functions had a period of 2 pi. Here's the multiples of 2 pi. Trying to think of two things in my head at the same time. And then let's say another one had a period of 3 pi. So 3 pi, 6 pi, 9 pi. If those were my periods, I would say the LCM here is 6 pi. That's the lowest common multiple of pi they both have in common. And that would be the period. All right, so let's start with sine. That one we should already know. What's the period of sine in radians? Yeah, right?
2 pi.
It's 2 pi. Now let's graph cosine squared all by itself and see how often it repeats. And then from that, I think we'll be able to figure out the period. Okay, this is how you type in cosine squared. Cosine x, close parenthesis, squared. What I typed in right there is what you see in that first box. It's very important that the exponent is outside the parenthesis. Okay. Right, I'm going to set a window from 0 to 2 pi and hit graph. Now, based on already knowing how wide that window is, I think we can tell how many times it's repeating. So this is 0. This is 2 pi. That means right in the middle is 1 pi. What does it look like the period is of cosine squared? How long before it does its thing and then starts over and does it again? Yeah? 1 pi. That's the period of cosine squared. Again, you're not going to have to graph that pretty soon. I'm going to show you a formula that does it for you. But I think the graph makes it pretty clear. It's 1 pi. All right, let me just pull this up a little. All right, so I got a period of pi. I got a period of 2 pi. The period of this whole thing is the LCM of pi and 2 pi. So, what's the least common multiple of 1 pi and 2 pi? Yeah, 2 pi. So now, when we type in that whole equation in y1, if you want to see exactly one cycle, make your window that big, from 0 to 2 pi. Now let's type the whole thing in. If you press second insert, you can just put the 2 in front of the cosine. Or if you want to just clear it and start all over, you can do that too. But that's a little faster. Plus sine x plus 1. Now, I just want the answers in one cycle. One cycle is 0 to 2 pi, so my window is actually fine. So let's hit graph and see what it looks like. So there's what the graph looks like. I take that, put it here, and trace it carefully. Now I take that and make a copy of it. When I copy it, it should line up perfectly if I put another copy of it right there. That's what your graph looks like. Right? That's 2 cycles. Okay. If you wanted to see what a third cycle would look like, you could put it right there. So that's the pattern of this graph. That's almost 3 cycles. It goes off the screen. Now, they want us to calculate where it's equal to 0. We haven't done that in a little while. Does anyone remember where I find that? Where it crosses the x-axis? Yep.
You just do second calc and then 0.
Yep, second calc 0. Pick a point to the left. Pick a point to the right. Do your guess. And we get an answer of 4.71. Tori, how often does that answer repeat? Every period. You can kind of see it right here. If I put the line in, maybe there you go. You can see that it's going to dip down and touch the x-axis once every cycle. And what's the distance between periods? 2 pi. So we can say that answer repeats every multiple of 2 pi, forward and backward. And that's it. That's how you rate your answer. Okay. Any questions on that? Now you might see in the book they do 2 pi k, 2 pi n. It doesn't really matter what letter you use. Okay, I'll show you that. Okay, let's look at this one. I don't think we're going to have to play with this one. There's no functions to higher powers here, so we should be able to figure out periods of both of these. Now, before I even do that, if I want to solve this like I did the last one, what should I get this equal to? Okay. I should get it equal to 0. I'm not saying you can't put this in y1, this in y2, and do an intersect. You can. But since we're practicing zeros, let's get it equal to 0. And this is one way to do it. Just minus the 3 cosine x to the other side. Gabe, how many periodic terms do I have on the left? 2. There's 2 terms there that are going to have their own periods. There was also 2 in this one. 1 is not a periodic term. That's a constant. Never changes. But that's a periodic term. And so is that. What's the period of tangent? Yeah. It's pi. The formula is pi over b. B in this case is 1. B has always been 1 in these problems so far. That's pi. Period of cosine. Yep. 2 pi. We just did something like this. The least common multiple of 1 pi and 2 pi is 2 pi. 2 pi comes up a lot. All right, so we've got the least common multiple. What that's going to tell me, how big of a window on the calculator do I set? Set a window that's 2 pi units wide. And I've already got it, 0 to 2 pi. Now let's type in our equations. Or equation, there's only one. So we got tangent x minus 3 cosine x. Now it might go off the screen. I don't really care if it does because I'm not looking for maximums or minimums. As long as I can see where it crosses the x-axis, I'm good. Okay, so how many times does it look like this graph crosses the x-axis per cycle? Yep. Yeah, 2. And if you notice, if you were to draw it and copy and paste this picture, this part right here would connect perfect to that part right there. And you'd get your picture. All right, let's find both answers. Second calc, intersect. Okay, I'm going to do the second one. If somebody else is closer to the first one and you can find that one, that would be helpful. I think I did intersect. I meant to say 0. There is no intersect here because intersect means you've got 2 pictures on the screen at the same time. I don't. So second calc 0. 2.13.
The first one's 1.01.
1.01. And remember, each of those answers is going to repeat every cycle. How about, Justin, what's the length of my cycle here?
I don't know.
Not sure?
No.
Anyone help him out? What's the length of the cycle? I think that's the first thing we found. Yep. 2 pi. Okay, so not too bad so far. All we had to do is really find 2 answers at most per cycle. Not bad. All right, before I do this one, I want to show you the pattern with how you can find the period of higher trig functions. So it all has to do with whether you're raising it to an even or an odd power. For tangent and cotangent, it doesn't matter. It could be tangent to any power, cotangent to any power. But if you're doing sine to an even, cosine to an even, secant to an even, cosecant to an even, or any tangent or cotangent, this is the formula you use to find the period. Yeah?
How do you find, like, earlier, like, you just knew the periods for the other ones, like
Yeah.
that?
Well, other people were saying them, yeah.
Yeah, don't really have to do that.
So they were basically doing this, either they had it memorized or they were doing this in their head. This formula was what they can use to do that. So we'll go back and look at the ones we just did, use this formula and see why it works.
So, because I don't have them memorized, can I just use that formula if
Yeah.
I need to?
Yep. There's two formulas. It's pi over b and 2 pi over b. I put b in absolute value because if b was negative, you never use it as a negative. The length of a period is a length. Lengths can never be negative numbers. Okay. So you either use pi over b, or the other cases you're going to have are sine to an odd, cosine to an odd, secant to an odd, cosecant to an odd. For those four cases, you use 2 pi over b. I don't know if you can read that. So most of the time you use pi over b. You always use it for tangent and cotangent. And you use it for everything else when it's an even power. The only time you use 2 pi over b is if it's sine, cosine, secant, or cosecant to an odd power. So now we've got this chart. It kind of helps us so we don't have to play with it. We can just figure it out using a formula, what the period is. We'll go back and look at one of the ones we already did now.
So like, for the ones that they're reading, you can just use either formula that corresponds to.
Yeah.
You should know.
Yep. So let me go back to one we did. Cosine to an even power. Okay. B is 1. B is always the number that's right in front of t. Cosine to an even power, b is 1. Let's go back to our chart. Cosine to an even power, you use this formula, and b is 1. Pi divided by 1, we should have gotten pi, and we did. We got it by drawing a picture. Now you don't need to do that. Okay. Let's look at this one. Tangent. There's no exponent at all. If there's no exponent, you always assume it's to the first power. So that's tangent to the first power, and there's a 1 in front of the x. Tangent to an odd power with a 1 in front of the x. Tangent to an odd power, there's your formula. There was a 1 in front of the x. Pi over 1 is pi, and that's exactly what we got. This is cosine to an odd power. There's no power. Cosine to an odd, and there's a 1 in front of the x. Let's go back to the chart. Cosine to an odd, and there's a 1 in front of the x. 2 pi over 1, 2 pi. And that's what we got. So this formula always works. Anyone else still need to copy down? I mean, you might be able to write that in a shorter way in your notes, but it's just how I wrote it. Okay, so let's look at the first one. Sine to an odd power, and what number is in front of x? Yeah. 2. Sine to an odd, and b is 2. What formula do I use when it's sine to an odd? Top one or bottom one? The bottom one. There's your formula right there. 2 pi over b. 2 pi over 2. So what's the period of sine cubed 2x? Pi. There's two things there that are altering the period. The cube and the 2 in front of the x. And we took into account both of them. So the period of that is pi. And it kind of helps if you just memorize the periods of the basic ones, so you don't have to look them up every time. What's the period of cosine? Yeah, wait. 2 pi. We've done this one a couple times. least common multiple of 1 pi and 2 pi is 2 pi. All the LCM is really used for is to set the window on your calculator. That's it. So set your window from 0 to 2 pi. Is it always going to be 2 pi? It might not be every time. But a lot of times it is. All right, 0 to 2 pi, we're good. All right, now we have to type all that in. So we want 3 sine of x cubed, 2x, sorry. So just insert it 2. 3 sine 2x cubed minus 2 cosine x. Minus 2 cosine x. And we're calculating the roots. Where does this equal 0? Let's hit graph. I don't care, that goes off the screen. Okay. How many times does it look like that crosses the x-axis? Yeah, 6. I already have all the answers written. Is there any question on how you find them? Second, I'll just do one of them. There you go. Second, calc 0. I'll do the one in the middle. Well, I don't know, the fifth one, I guess. That one, and we get 2.65. Okay. Plus period times n. So let me write them all out. Yeah. So you're going to get one at 0.5. You're going to get one at 1.25. 1.57, 1.89, 2.65, I think that's the one I just did. Yep, 2.65, and 4.71. And they're all plus the period times n. So 2 pi n. There's all your answers. If you did second calc 0, you would find that those are all your answers. Any questions on that one? Probably more of an annoying one. I wouldn't put one on a test where you got to do the same thing 6, 7, 8 times. Maybe 2, 3, 4, but 6. If you can do it 3 or 4, I think you could probably do it 6 times. All right, so solving inequalities is pretty much the same idea as solving equations, except when you write an inequality, your answer is not x equals a number. It's usually an interval, like between 2 values. So go about it exactly the same way. Find the solutions just like it was an equation, and then take into account that it's an inequality. So what that means is our answers are going to be intervals. So we'll be writing parentheses, brackets, things like that. A couple things to remember. If you include the left end of your window, you don't include the right edge. Like if you set a window from 0 to 360, don't include 0 and 360. Right? When you're finding solutions, if your graph looked like this, say, here's your window on your calculator from 0 to 360, and it looks like this. And I said, how many answers are there per cycle there? I would say 1, 2, 3, 4. That fifth answer, because it's right on the edge of the screen, is actually a repeat of the first answer. So there's only 4 answers in that window. Okay. So keep that in mind. Vertical asymptotes, those might come up, but if there's a vertical asymptote, it's going to be pretty obvious what it is. It's going to be like pi, or pi over 2, It's going to be a very easy one to find. It's not going to be an obscure number. Right, so I want to solve where the sine function is less than the cotangent function. So we're going to do it just like it was an equation. Put sine in y1, put cotangent in y2. If we did it as an intersect problem, or if you want to do it the way we've been doing it, get everything on one side first. So Gabe, let's do it the way we've been doing it. If I wanted to put everything on one side, how would I do that?
Subtract one from one side, bring the other.
Yep, just subtract. Okay, so let's graph what's in blue and see what we're looking at. Actually, before I graph it, I should figure out the period. Anyone think they can tell me the LCM? Yeah, sine is 2 pi, cotangent is pi, 2 pi and pi, LCM is 2 pi. I think when there's no exponents, it's a little easier. When you start getting in exponents, you might need that chart. All right. So window 0 to 2 pi looks good. Sine minus cotangent. Well, there's sine. How do I type in cotangent? Blake?
1 over tangent.
Yep. 1 over tangent. There's sine minus cotangent. Okay, let's see what we're looking at. Now, to me, it's pretty obvious there. I'm thinking I see a couple vertical asymptotes. If you're not sure, you can go a little higher and lower, but let's double height and how low. But I mean, to me, it's pretty clear that there's 2 asymptotes per cycle here. I say 2 and not 3 because there's one right on the edge of the screen. Looks like there's another one on the edge of the screen as well, right there. That's a repeat of the one on the left edge. Can't say that they're different because if you put the graphs next to each other, they would be the same. And I think there's one right in here. About like that. Now, the one in the middle of the screen, that's the hard one to figure out sometimes, but it's right in the middle, exactly in the middle, and we know the edges of the screen, 0 and 2 pi. So finding what's in the middle shouldn't be too hard. All right, so let me trace where the answer is. We're looking for where this graph is less than 0. That's going to be down here. Now, when it says less than 0, does that mean I can include 0 or not include? Yeah, not include. So I'm going to put an open circle. So I remember, don't include that. And where else? From here up to here. So what I have to do is describe those 2 things in red as intervals, okay, on the x-axis. Where does, for that graph in red, what's going to be the left edge? Like how far left does that graph in red go? Rob?
Doesn't hit 0, but it goes really close.
It gets very close to 0, yes, but it never hits it. So that graph in red is from 0 up to, now I need to use my calculator and find out what that circle is. So second calc 0. Okay, I don't know where I am right now, so I'm looking here. 3.14, and I'm down at negative. So I want to bring my graph to the left. I want to get over on this other curve. Now I can see my cursor. So we go from here, and that curve in red, the first one stops at 0.90, and I cannot include it because of that. So that's my first interval, from 0 to 0.9. Or I have another interval. Look at the second red curve. How far left does that one go? It's hitting an asymptote. So the question is, where's the asymptote? Yeah.
It doesn't hit pi.
It doesn't hit the pi, right? If you try to go to your table and type in pi, you get an error. So there is an asymptote at pi. So it gets very close to it. Never reaches it. And it goes right up to that other open circle, which will be another parenthesis once I figure it out. So second calc, 0. Just keep pressing right, it'll jump to the other curve when it gets there. Go. And that second interval goes up to 5.38. Now, last thing we have to do is explain that these intervals keep repeating every cycle. So what would I want to put on each of these intervals to show how often they repeat? Yeah? Yeah, it's the same thing you did. This isn't really formal notation, but you can just put plus 2 pi n on each interval. Meaning if you add 2 pi to every single number here, you'll get the next set of answers. And if you add 2 pi again, you'll get the next set. Okay? That's what they're looking for. Yeah.
Does it matter if you put 3.14 or can we just put the same?
No, you could put pi there if you wanted. I just figured since we didn't do exact answers for any other number, I didn't do an exact answer for pi either. Okay. Question on that one? All right, so we're going to do this one, and it says to do it a little different. It says leave it alone. Don't bring everything to one side. Just graph it the way it is. So we're going to graph sine 2x, and then I'm going to put x squared minus 1. What shape is this graph on the right going to be? Yeah, it's a parabola. It's a parabola shifted down 1 unit. So when I want to find the period of this, there's only one periodic term here. Parabolas aren't periodic. Periodic means it's sine, cosine, something like that. What's the period of sine 2x? Pi. It's 2 pi over 2, which is pi. All right. So let's graph it and see what we got. Sine 2x and x squared minus 1. Now, I'll set it from 0 to pi, and let's see if that works. Are we seeing a complete picture of the parabola? No. So I'm looking for where the trig function is above the parabola. Well, I think it's above to the left a little bit too, but I can't see over there. So I'm going to do this one a little different. It doesn't have to be symmetrical, but I need to see to the left more than I am now. So there's that. And now I can see pretty clearly when the graph in blue is above the graph in red. It's going to be right in this section right here. That's where the graph in blue is above the one in red. Now, is that going to happen again off the screen later on? Why not? It seems like these patterns keep repeating off the screen over and over. Why Why won't I see something like this off the screen?
The parabola goes infinitely up.
Yeah, the parabola just keeps going up. Parabolas, they don't look like this when you draw them. They're not periodic. They don't repeat over and over. You get one parabola and that's it. So the answer is from here to here. Why did I put filled in circles this time? You can just barely see why. But
Because it's greater to and equal.
it's greater than or equal to. So on this problem, you would calculate an intercept. Let's say you've got the coordinate AB. I don't know what it would be. So you got that. And then here, you get the coordinate CD. The answer to this problem is from A to C. Whatever you calculate for A and whatever you calculate for C on the intercept. Okay. Make sure you use brackets though. Don't put plus 2 pi n on that. Doesn't need it because the parabola never repeats itself. It just keeps going up. Any questions on that one? Okay, it's a little different because one of them was periodic, one of them wasn't. I'm not really worried about example 7. That's just something else. Okay, so the last thing we'll look at is when you have a double inequality. Kind of the same as a single inequality, except you've got 3 things you're going to graph, and you're usually looking for where something is between 2 other things. So you just graph all 3 functions as separate graphs, and then interpret what you're looking at. Color is very helpful here because you can see things that you wouldn't be able to see if it was black and white. If you have one that's black and white, that's okay too. You'll see why the color is helpful in a second. Okay, so let's solve that. I want to know where x sine x is sandwiched between 2 other things. Okay, so let's graph all 3 of those on separate graphs. We've got negative x sine x, and positive x. When you put a number in front of a trig function, what does that do? Like 2 sine x or 5 sine x? What kind of transformation is it? Yeah?
A vertical stretch.
It's a vertical stretch. This is a variable vertical stretch, which means the amount of stretch is constantly changing, which basically leads to looking something like this. So the further and further away you go, the more and more vertical stretch you get. Get closer and closer to 0, very little amount of vertical stretch. So it's a variable vertical stretch. Okay, let's do zoom 7. And let's kind of color coordinate this. So x sine x is in red. Negative x is in blue. And positive x is in black. So we're looking for where the graph in red is above the graph in blue, but below the graph in black. Okay, and let's do zoom 7. All right, and let me zoom out. It's going to make it a little easier to see. There's your graph in red. And there's your graph in black. We're looking for where the graph in red is above the blue, but under the black. Where does that happen? Where is the graph in red above blue? I know blue is hard to see, but below the black. Yeah.
0 to infinity.
From 0 to infinity. Everything to the right. Yeah. And it does say including. So from 0 to infinity. It'll be above the blue and below the black. Okay. Next one is where the color comes in handy, comparing it to this one. Let's graph the negative absolute value and the positive absolute value. The middle is going to stay the same. So I'm going to do math, number, absolute value. And I should put negative in front. And do the same thing as a positive. Math, number, absolute value. Okay, let's write down the colors again. So the middle is red. The blue is my negative x. And the black is positive x. Let's compare that to the picture we just did before. If somebody was looking at these two pictures, right there, and they were black and white, or the person was colorblind, one or the other, what would be the difference between those two pictures? Yeah?
If they were colorblind, they would see a difference.
There is no difference. You can't see it. So black and white, they kind of look the same. But when it's in color, you can tell that the diagonal that goes up and to the right here is one continuous function. It's all black. There really isn't a diagonal here. It just looks like a diagonal because you have two V shapes with the vertices kind of touching. All right? So they do look different. That's why I think the color comes in handy. All right, so let's see if we can finish up and answer that question. So I'm looking for where the graph in red is above the blue and below the black. Where is the graph in red above the blue but under the black? Yeah, everywhere, the whole thing, from negative infinity to infinity. That's always going to happen. Now, if it was the opposite, if it never happened, you could just say no solution. But that's everywhere. Okay, so that's how you solve periodic equations with higher powers, and then kind of some special cases with double inequalities. All right, so homework tonight, it's just a bunch of different ranges. So 5 through 7, 11 through 15, 19 to 25 is just the odds. 29 to 31, that's all, and 33 to 37 is just the odds. So we'll look at that tomorrow, and that pretty much finishes up this topic. Okay, so we're done with solving trig equations for now.